Okay, so for anyone who cannot import Excel files into your eViews, just click on any cell and then just type, just use the Control A, just kind of like select everything in your Excel file like this. They're gonna kind of like highlight all of the data on Excel, right? And then you just copy it. So once you're done, just go to the program called Notepad. So this way you can transform the file type from Excel to text file. So after you open Notepad, just do right click and then go to paste. Or you can just go to edit and go to paste. You can do both ways. Either one is fine. And you will see that you already copy and paste the data from Excel to Notepad. And then just save it. Just go to save as or save whatever is not different. And then just type the file name that you want. Oops. So here. So now you already transformed from Excel to text. And once you go to eViews, you can just import this text file into eViews instead of Excel. Okay, this is how to fix it. If you cannot import Excel file into your eViews, just transform it, just change the file type from Excel to Notepad. Okay, so now let's go back to our eViews. We are going to use waste file here. So this is the file that you are familiar with. We use it many times, right? So I would like to request wage on age, education, experience, and experience to here, and also IQ. Okay. And one thing that I would like you to do after you get problem set from Dr. Sivapong, I recommend you to just read a whole problem set, because I'm not pretty sure that every variable that he gives you, you will use all of them. For example, like in this data set, you can see that we will use just only a few variables here. We will not use everything in this data set, right? So if from the problem set, you see that, okay, we will not choose every variables in there, I recommend you to just save it. Otherwise, you have to waste your time, kind of like click on the variables that you would like to use, right? So if you remember like how to save it, for example, I know that I'm going to use wage variable, age, education, and both experience variables here and also IQ every time. Like for multiple times in the problem set, I'm going to save it separately. So one thing you can do is that just open them together, right? Just click on wage, click on any variables that you would like to use it, and then do right click, open it as group. And if you remember that we are going to name it, there is a menu tab on top, right? Name it whatever you want. So I'm going to name it use. So after you click OK, try to close this window and just take a look at the window of variables names, right? You will see that they already have like generate another one called use. Open it is going to be all the variables that you already selected, right? So this time, I'm sorry, I mean like if you do like this, it's gonna save your time to do problem set, because if you know that, okay, these are all variables that we are going to use multiple times, just save it. So if you do just only one click, that will give you just the variables that you want. Don't have to waste your time click on it many times. Okay. And if you would like to run regression from this window, you can just go to prop, right? And also have make equation here. And again, don't forget to check it. The first variable here will be your dependent variable, right? So if you check everything and this is the model that you are going to run regression, just click OK. And this is going to be your first result. This will be the step that you have to do on your project as well, right? I just try to rebuild everything for you. Let's think about your project. You know that this is all, you already have all variables that you would like to find their relationships, right? And then once you're done regression, you can say that, okay, not all of them are significant. So first, you have to check whether or not your model has any issues. The first thing you should check is the multicollinearity, right? So can anyone tell me like how to check the multicollinearity? There are a few ways to check it, right? So what you have done with your project, if you suspect that your model has multicollinearity issue, can anyone tell me? Yes, to do correlation. That's right, to do correlation matrix, or you can do VIF test, right? So first, I will go with the correlation matrix. Okay, so after you opened all the variables that you have, you can just go to View, and then go to covariance analysis. Right? And again, just take it out and choose correlation instead, and then click OK. And then try to find which variables that have more than 0.5. Right? So in this case, you see that, okay, the experience number 2 and 8 have correlation more than 0.5. Actually, like, there is no right or wrong if you would like to use more than 0.5. Some of you might use 0.8 or something like that. Okay, it depends on like rule of thumb that you are using. But anyway, you have to explain when you answer our questions. For example, like we might ask you which value that you used as a cutoff for a high multicollinearity, right? So in this case, you might think that, okay, just 0.5 is fine. But if you think that you would like to use 0.8, just explain us. So we can see that age and experience number 2 here have a very high correlation. Right? So we suspect that, okay, both of them have high multicollinearity issue. So that's one way. Another way is that you can try to find the VIF test, right? And how to do VIF test. So if you take a look at the lecture that you learn in class, you have to do auxiliary regression, right, for each independent variables. And then use this formula to calculate the VIF. Right? For example, like, okay, from here, I suspect that age and experience number 2 might have a high multicollinearity. So I'm going to do the auxiliary regression for age. So I can just click on age, right? Age is going to be my dependent variable. And then click on any other independent variables here. And again, just do equation. And then click OK. So this is going to be the auxiliary regression for age. Right. And the things that we are going to use from this auxiliary regression is the R-square. You can see that we have R-square here. So you can just use the calculator that you have to calculate the VIF, or you can use the command, just type the command in eViews. Right? The command that we are going to use is scalar. And then I'm going to name my new variable here as VIF underscore age. You can name whatever you want, okay? And then use equal sign and just type the formula that you would like to calculate. So here is going to be 1 divided, right, by 1 minus R squared that you already have here. And please be careful if you would like to type the command in eViews, because we are going to use the result that we have calculated. It means that once, for example, like if you're already done with this auxiliary regression, and then you did not calculate the VIF for age, but you do another auxiliary regression, you will get different R square here. And when you type the command, they are going to use, like eViews is going to use the different R square. It's not the R square from this equation, so please be careful, okay? It means that if you would like to type the command in eViews, you have to do it after you are done with each auxiliary regression. So in this case, we are going to use add and type R square. So eViews will know that, okay, you are going to use the R square from the result that you have got. So if it's too small, let me use PowerPoint here. This is the command that I typed. So the first term is different. We normally use series, right? But series is like a multiple numbers that you would like to generate. But scalar is just one number, one value that you would like to generate. And just type the name of that variable and use equal sign followed by the formula of the VIF. Okay, so once you then just press enter. There will be another variable in this window. Just click and see it. So this is going to be the VIF of age. And if you look at your lecture, I think the rule of thumb is just only 10, right? But here, the VIF of H is about 40, which is pretty high. It means that H has already have, I'm sorry, H has already, H has the high multicollinearity issue here. So that's one way to calculate VIF. But I also have an easier way for you. So once you're done with your regression here, you can just go to View and then go to Coefficient Diagnosis here. So it will already have the variance inflation factors, or the VIF. You can just click on it. Oh, I'm sorry. It's supposed to be the original regression that you run. I'm sorry. So it's supposed to be this regression. The weight is education, both experience and IQ. I'm sorry, it's not the auxiliary regression. It's supposed to be the original, like the first regression that you run, okay? So once you're done, just click on View and go to Coefficient Diagnosis. And look at the centered VIF here. So just click on the VIF edge that you already calculated and let's compare. You will see that you will get the same VIF value here. So if you cannot remember how to calculate VIF by typing a command, you can just go to View, Coefficient Diagnosis, and then go to the variance inflation factors. It will already calculate it for you and use the center VIF, okay? I'm not pretty sure which questions Dr. Silverphone will ask you. He might ask you to calculate manually. It means that you have to show him how to get each VIF value. But if he doesn't ask you in that way, you can just use the command that it will already have. Just click on it and everything will show up. Right? And now you know that there are two variables here that have a very high VIF. It means that both of them can cause a high multicollinearity issue. How to solve it? So if you know that two of them already cause you a high multicollinearity, the way to solve this problem is that you have to just delete one of them out, right? And how do you know that? Which one we should keep it? So let's think about, we are going to delete H out first, and then we are going to delete the experience number 2 out. And again, you can see that we use this data set all the time. So I'm going to just click on it and go to proc and then make equation. But now I would like to delete H out first. I would like to see if I delete H, if I just drop H, how the results would be. So right now I'm going to regress weight on education and both experience and IQ. Then click OK. And I'm going to freeze it just to compare the result, because we have to pick, right, that we should drop H or drop experience number 2. So we have to compare which model is better. So once we're done with the first, we are going to just drop experience number 2. And again, go to proc and make equation. And now try to drop experience number 2. and then click OK. So we have both results. So first, let's take a look at the side of each coefficient. You will see that both models give you the same side of each coefficient. Okay, and then let's take a look at the probability here. Okay, so both models give you like all significant variables, right? And now another thing that you have to take a look is that the R square. Even though like this model has, I'm sorry. So this model has a little low R square, right? This model has higher I square, the same as adjusted R square. So the second model has higher adjusted R square. And also you have to take a look at the EIC, right? If you look back at your lecture, Dr. Sivapong already explained it. Where is it? Oh, I think it's on week 8. I think he already explained about the AIC and another, this one. Yep. The criteria to take a look which model is better. Another thing is the AIC and SIC, right? So we already have it here. AIC for the first model is around like 14.6 something. This one is a little bit lower, right? It's 0.665. This one is 0.666. Also for the SIC, the below one. So this one is a little bit, the second model is a little bit lower. So the lower is the best, right? Lower is better. It means that basically, even though both models give you all significant variables, we should pick the second model, which means that we should delete the experience number 2. Because the R square is a little bit higher, adjusted R square is a little bit higher, AIC and SIC are lower than the first model. Do you have any question about it?
Professor, for those variables that are, let's say that like we check the multicollinearity and like it's also insignificant in like the first, the first result, then we can just delete it right away, right? Even if we test the omitted variables also. Like, is it alright to delete something that is doesn't cause any issues and then is also like insignificant?
Oh, you mean like, for example, like after you delete the one with the high multicollinearity, and then you also have something with the insignificant variable?
Oh,
Is that
no,
the
no.
case?
It's like when we test all of the variables, right? And none of them has any issue, no multicollinearity. It's just there, like it's not even significant also. Can we just delete it out of our model?
Yes, sure. Because the omitted variable here, it means that the variable that you are considering has a correlation with other independent variables and also have a correlation with dependent variable, right? So if you run your regression and then, for example, like just assume that the experience here is insignificant, it means that the experience doesn't have any effect on weight. There is no correlation between weight and experience, right? So even though you drop it, it's not going to cause omitted variable. because experience is not correlated with weight.
All right, thank you.
You're welcome. So that's a good question because that is another point that I would like to explain. Right? So we know that, okay, this is our best model for now. Right? So after we are trying to fix a high multicollinearity issue, we already dropped it, the experience number 2. So this is going to be our best model after we solve the multicollinearity. So from this one, you see that all variables here are significant if you just accidentally drop one variable out of your model. For example, like we are going to drop experience here out. So I'm going to freeze it and then trying to run another regression without experience. So now we are going to drop both of them out, right? For example, like you know that the model on your left hand side here is the correct model, but you just drop experience accidentally, right? So that's why you got your right model here. So once you accidentally drop experience, it's going to cost you an omitted variable. Why? Because you know that experience here might have a correlation with one of these independent variables. And also, like from the correct model, you know that experience has a correlation with weight, your dependent variable. Right? So let's go back to your lecture. You know that omitted variable can be like this correlation. So if you have two independent variables, x1 and x2, right? And both of them have correlation with your dependent variable. And x2 also have a correlation with x1. So if you just drop it accidentally, it's going to cause an omitted variable. So that's the case of the omitted variable. Right, so let's go back to your friend's question. If we assume that experience here is insignificant, so if the experience is insignificant, it means that experience doesn't have any effect on weight. So there is no correlation between experience and weight, right? So if you drop it, it's not going to cause an omitted variable, right? Because there is no correlation here. Even though like experience might have correlation with other independent variables, but experience doesn't have any effect on weight. So once you drop it, it's not going to cause an omitted variable. Is it confusing? Do you have any question?
อาจารย์ครับ
Huh?
When we check the correlation problem, do we have to include the dependent variable inside?
You mean like for the multicollinearity, right?
Yeah.
No, actually you don't have to. Because the multicollinearity issue, we are considering among independent variables.
โอเคครับขอบคุณครับ
So one thing I would like you to see is that we are going to compare coefficient between these two models. So the right one, the right result here is going to be the result after I drop it experience accidentally, right? So this the right model is a wrong one. So you can see that the coefficient of age is a little bit higher than the left one. So this could be a positive bias, if you remember that. Why it could be a positive bias? So we are going to go back and check the correlation again. So the experience, right, and age is here. The correlation between age and experience is a positive correlation, right? 0.49 is positive correlation. And also the experience that we drop it accidentally has a positive correlation with weight. It's about like 0.002 something. It means that experience has positive correlation with weight and also has a positive correlation with age. So go back to your lecture. Oh, where is it? Oh, this one. Okay. So here, so if Z here is the experience that we accidentally drop it, Z has a positive effect on Y. Y here is weight, right? And also age and experience are positively correlated. So that's why it caused positive bias. So positive bias can see from a bigger coefficient in the second model. It means that once you dropped experience accidentally, it caused a positive bias. It means that, so normally like the right one should be around like 14, but because of the positive bias, so it has a little bit bigger coefficient. And the coefficient here is biased coefficient because of the omitted variable. Is it clear? Does it make sense? Okay, so we're done with omitted variable and multicollinearity. So if you know that this is our base model, right? The one with age, education, experience, and IQ. And another thing that you have to check is the heteroskedasticity, right? And again, I already told you that if you, you can check heteroskedasticity roughly by plotting some graph, right? So we are going to go back to the command. I'm going to use scatter pair. I'm trying to plot scatter graph between some independent variable here and dependent variable. So I'm going to consider a graph between education, my independent variable, and weight, my dependent variable. If it's too small, it's going to be this one. Scatter pair is for a scatter graph. And then education here is going to be my first variable because I would like to put it in the x-axis, followed by the second variable that you would like to put on y-axis. It doesn't have to be, oh my God. It doesn't have to be your independent variable. It can be anything, but you would like to put this variable on x-axis and the second variable on y-axis. Okay, and I'm going to press enter. So you would be familiar with it. You can see like the data kind of like spread out. Once you have higher education, the variation of your weight would be like bigger than you have lower education here. So this is kind of like not a constant variance. So we might suspect that, okay, between education and weight may cause us like a heteroskedasticity issue. Right? But the formal way that we can check is just to have some test. So after you run regression, just go to view and go to residual diagnosis. Just go to heteroskedasticity test. And again, we are going to use the BPG test. You can use the BPG test or white test, whatever you want. It doesn't matter. For the BPG test, just click OK. And we are going to take a look at the observations multiplied with the R-square. And take a look at the probability of the chi-square that is calculated from the observation multiplied with the R-square here. So if the second row here, the probability is less than the significant levels that you set. For example, in this case, if you set a significant level at like 0.05, for example, so of course the probability here is significant. And your null hypothesis is the homoskedasticity. If the probability is significant, it means that you can reject your null hypothesis. So if you reject your null hypothesis, it means that your data have a heteroskedasticity issue. So please be careful when you check about hetero or homoskedasticity. It depends on the null hypothesis here, okay? Because eViews already said that null hypothesis is the homoskedasticity. So if the chi-square, the probability of the chi-square is significant, it means that you can reject your null hypothesis. And it means that the alternative hypothesis would be heteroskedasticity. So if you reject the null hypothesis, so your data have a heteroskedasticity issue. Okay. The same if you would like to do with the white test, you will get the same result. So for the white test, again, just take a look at the chi-square of the observation multiplied with the R-square here. You still have pretty low probability. It means that you can still reject your null hypothesis here. So your data have heteroskedasticity. And how to fix it? We are going to do robust standard error. Right? Click yes, and again, go to view, make equation. And for this window, just go to option and click on the Huber white. And then click OK. So I'm going to, I'm going to freeze it just to compare the result. without robust standard error. Okay, so the left hand, we already did the heteroscedasticity, just trying to fix it, right? And the right model is kind of like just the normal ORS. So the things that is going to different is your standard error. You will see that all the coefficients are the same. The things that are different just standard error. And I told you that once the standard errors change, it's going to affect your t statistic as well, because the t statistic is from dividing the coefficient with the standard error. So once your standard error changes, your t statistic also changes, and it's going to affect your probability as well. For example, like a variable here, you can see that the probability of the left model is kind of like higher than the right model, right? Because your t statistic already changed. And once we fix the standard error, we may check again whether or not we still have the heteroscedasticity. And the way to check is still the same step. Just go to View, go to Residual Diagnosis, and go to Heteroscedasticity Test, and then click OK. You still see that the chi-square, the probability of the chi-square here is still significant. It means that we still have heteroscedasticity. So in this case, it might be a problem from the misspecification. I already told you about it, right? So what should we do? We are trying to transform our model. So the things that we already did is just the level. So our dependent variable and all independent variables are at like the level. We already used that unit. How about we are trying to change it from level to natural log? So I got some emails from your classmates about like, how about if we are trying to fix it, but we still have heteroscedasticity issue, and your model cannot take natural log. So I have to say that you have to let it go. You have to let it be like that. Okay. For example, like if your variable are already in percentage, you cannot take natural log into it. It means that you cannot fix anything. You cannot transform into like any form. But in this case, we have just the weight in dollar, right? So I'm trying to just might change from level to natural log here. So if you remember, I'm going to use the series to transform weight to natural log weight. So this is going to be the command that I type. So I think this one you should be familiar with it. So just type series, right? And then type the name of the variable equal to the log. So log in EBILS is a default as natural log. And then just type the variable that you would like to take log into it. So once you're done, press enter. So you will have another new variable here. So I remember like in my lab session, I'm not pretty sure, like a week ago or 2 weeks ago, that we talked about heteroscedasticity. I showed you that I take a natural log into weight, right, my dependent variable, And I also take natural log into my independent variable. And I was trying to do something like level log or log level models. And I also got some emails that is it possible to do log models? You can do that as well. Okay. Just do whatever that you can fix the heteroscedasticity. So in this case, I'm going to just use the natural log weight as my dependent variable and use other independent variables as the level. The thing is that you already have use, right? So use is the data set that we already saved. But if you don't want to click like select too many variables, you can just click select only two, just the use one and the natural log weight that you just generated it, and then open it. They will already combined between the data set that we already saved and another variable that we selected, right? And then just go to proc and then make equation. But you have to be careful because they are going to kind of like order variables in a weird way. You have to kind of like arrange it. Like in this case, because we would like to request natural log weight on age, education, experience, and IQ. So this will be our model. I mean, like basically, if you just open the data set that we used, once you would like to generate equation, it will kind of like include all variables that have in the data set that you selected. So it might save your time, but you have to be careful. So every time when you would like to estimate the equation, you have to check every time that this is the equation that you would like to estimate. Okay. And then this is the estimate. This is the equation and the estimate. So my dependent variable here is going to be natural log weight, right? And I request it on other independent variables here. And then I would like to check on the heteroscedasticity. So now we cannot reject our null hypothesis here. It means that right now our data don't have heteroscedasticity issue. And all variables here are significant, which is good. So this might be my last model. I think that would be the best one. However, there is another way that you can check whether or not this is the best one. This is the best model. You might take log for both. So this one, I did log level, right? You might try level log or log, and then trying to compare about the significant, like the numbers of the significant variables, compare R square, adjusted R square, AIC, and SIC, and just pick the best one. Okay, do you have any question?
Professor,
Mm-hmm.
so for the Huber-White thing that we did, right? We only do that in case that we cannot reject the part like hetero or like we cannot reject the alternative hypothesis, right?
We
With the Huber-White equation.
You mean this one, the white, right?
No, I mean like when we see that there is the like in Bush Pagan, right?
Mm-hmm.
And then we see that like is already there is already homoscedasticity, there's
Mm-hmm.
no issue, then
Mm-hmm.
we don't need to like adjust the thing, right?
Yes, you're right.
Okay.
อาจารย์ครับ
ค่ะ
do we need to give the reason that why we use PPT, why or why we include something,
I mean,
or
like, it's,
you can
mhm.
or I can use anything?
You can use anything. It's going to be the same.
Okay, ครับ I think
Yeah,
that
yeah.
it have some different for the data that suit with that or not suit with that.
I know. Actually, like, basically, you will get the same result.
โอเคครับขอบคุณครับ
ค่ะ. So that would be all for cross-sectional data. So I'm going to review again. So after you have the data set that you would like to use, you would like to estimate, right? You already set the equation. So first thing that you have to be concerned is about the high multicollinearity. So how did you know that? You have to run regression at the beginning, right? Just do the first regression. And then let's try to check the correlation of each independent variable pairs, like a pair of each independent variable, right? You can check that correlation or maybe just check the VIF test. It depends on which one is more convenient for you. And if you find out that your data have a high multicollinearity issue, you can just have to go to fix it by delete one of them out. Or if you have more than one variables that have a high multicollinearity issue, you just have to try. For example, like in our sample, there are just only two variables. But if you have three, you have to try delete one of them out at a time and compare the models. Compare the results that you have, which one could be the best model at that time. And then after you get the better model, so another one is that you have to check for heteroscedasticity. And one thing that I haven't explained yet is about the dummy variable. This one is also important. For example, like if I would like to add another dummy variable is the race of people. So in this case, it's going to be the variable of black one. And I'm going to select three of them. It's going to be the data set that I already saved, and then natural log weight and the rest of people. And then just open it together. If you are lazy, you can just kind of like name another file. So if you are going to use that more often. And then I would like to estimate the equation. I would like to request natural log weight on people race and age, education, and just the experience and the IQ. Then I click OK. So this will be your result. And if you would like to generate it as a graph, just trying to see, because you know that if you already have a dummy variable, you can see the different intercept, right? But before we generate a graph, I would like to warn you another thing is about the interpretation. Please be careful when you interpret the coefficient of dummy variable. You have to compare this variable to a reference group. So in this case, our black variable here is whether or not the individual is a black people. So our reference will be white people. It means that the coefficient is a negative. So you have to say something that black people will have less weight than white people. You have to compare, okay? So if you have more than two dummy in one category, for example, like you already learned about regions, right? We have North, central and south, for example, you know that if you have 3 dummies about regions, you cannot put them together in one model because it's going to cost you a perfect multicollinearity, and it will not give you a result.
Professor, another question.
Sure.
For the multicollinear part, it's like when we do the correlation, right? Like when we test our correlation in, like, let's say descriptive or in like the model, do we do the correlation with the log form already, or do we just do it with the original data without any like log or level?
It depends. For example, like if at the beginning you would like to use the level model, and if you would like to test the multicollinearity issue, you have to do it with the level. But if you think that your original model, you would like to do something about natural log form, you can just test from the natural log form. So it depends.
So that's for the correlation, right?
Yes.
The correlation metrics. So it would be like ln form is okay also, right?
Yes.
How do I say? Like in the correlation metrics, we don't use the original data, but we can also put in the form of it.
Yes. For example, like if your original model is the natural log weight. So I mean, like at the beginning, you think that you would like to use natural log weight, right? And then you also have the level of the education, for example. This is the level 1. This is the log 1, right? And this is the level. So you can just do the correlation matrix between them and just check whether or not that correlations is higher than 0.5 or 0.8. You can use this as well.
All right, thank you.
Okay. And then let's go back to our dummy variable. So in this, our estimation, we have a race of people, right? So you know that if people is black, I will set it as 1. And if they are white people, it's going to be 0. So white here will be best group or reference group. I already told you that if you would like to interpret the result, you have to compare your coefficient with the reference group. But if you have more than 1 dummy variables within the same category, for example, like regions that I already told you, you have north, south, and central, right? I already said central. And here will be like if people living in north is going to equal to 1, and if not in north, it's going to be 0. The same as south, it's going to be 1, 0, and central is going to be 1 and 0. And you know that you cannot put all these dummies together because they are going to cause a perfect multicollinearity. Means that if you would like to estimate your equation, it must be 1 category drop out of your model. So in this case, I'm going to drop central. So if you know that you already dropped central, central here will be your reference group. So if your beta 1 is positive, for example, it means that people who live in north, so if our dependent variable is weight, it means that people who live in north will have higher weight than people who live in central. So for the beta 1, it's going to be a comparison between north and central. And for beta 2, it's going to be between south and central. don't forget to compare your result with the reference group. Okay. So let's go back to our e-views. So after you got the result, and I would like to show you that, okay, if we have just a dummy variable and how to plot a graph to show that different races might have different intercept when we plot a graph, right? So first, I'm going to predict weight. So just go to proc, right? After you run regression, finish running regression, just go to proc and then go to forecast. So they already set a default like a long range F. So F here is for forecast. So if you don't want to change the name of this variable, just click OK. And then I would like to see a relationship between long wage that we already forecast, like the forecast of the national log wage, and the education of people. And I would like to separate between the relationship, this relationship of the black people and the relationship of the white people. Right? And again, follow the command that we already typed. I already told you that if we would like to plot a graph, the first variable that we would like to select will be on the x-axis, and the second variable that we select will be on the y-axis. So I'm going to use the national log wage that we already forecast on y-axis. So I'm going to click on the education first, followed by the long wage F, and then open it. So let's go to view, go to graph. So we normally select it, right, which graph that we want, but this time, because we would like to separate the data by race of people. So just go to the top of this window, just click on the basic graph and select the categorical graph instead. Again, I'm going to plot scatter graph. Just click on scatter. And of course, we have to select variables that we would like to separate the data. So in this case, it's going to be race of people, right? It's the black variable here. If you would like to separate the data more than one category of the variable, you can just type more than one. For example, like I also have another dummy variable called urban. It means that people who live in urban or rural area. So if you like to separate data into like by race and by the place that they live, you can just kind of like type black and then urban, for example. So they will separate the intercept into 4 different categories. It's going to be like black and urban, black and rural, white and urban, and white and rural. I already told you, right, when we talk about the dummy variable. But in this case, it's going to be just the rest of people. Then you click OK. And again, because I did not choose the linear line, you can select on the fit line as well. Just click on regression. Regression line. So they will give you like a linear line as we saw before. So the blue line is going to be a linear line for the white people, and the orange line is going to be a linear line for the black people. Right? So basically, this is just the predicate weight separated by race of people. However, if you like to do an interaction term, for example, like between education and risk, you can just type again, use series, and then just type the name of variable that you would like to name it, and then use star sign as the to multiple two variables together. So the last term is just the education. I would like to do interaction term between education and rest of people. So once you're done, just press enter. You will get another variable here. And again, I would like to request language, on age, on race, black education, education, black experience, and IQ. So equation, click OK. Yep. And again, just go to prop, go to forecast. And I'm going to use forecast number 2. And again, if I would like to plot a graph between predicted wage and education, just go to graph. Again. Going to separate data between black and white people, and also click on the fit lines, then click OK. You will see that once you have an interaction term between dummy variables and the any racial variables, you will have different slope as well. Because right now, when we talk about the education is also depends on the race of people. So that's why you have different slope. Do you have any question about it? So this is all. Oh, you have studied for the cross-sectional data. Okay. Do you have any question?
Professor, for like the presentation, do we like is it necessary to show the scatter diagrams of everything?
You don't have to. I mean, like as I told you before, you have limited time, just only 15 minutes. So you have to kind of like arrange what you are going to present us. So basically, you should have an introduction, you should have a theory, you should talk about theory and data and your model, of course. And I think once you talk about how to solve the problem that you have, for example, like multicollinearity and heteroscedasticity, I think 15 minutes should be enough for that. I'm not pretty sure that you will have a time left to talk about the scatter graph or something like that. I'm not pretty sure. You might try to present first. Just try to talk a little bit about it. I don't know if you have time left. Yeah, maybe why not? But if you don't have time left, I think I don't recommend you to talk about it.
All right.
And also again, I got an email about the text in the presentation. One of your friends asked me that whether or not we should kind of like put everything is kind of like so many text in presentation slide, and I don't recommend you to do that. So in your presentation slide, you should have just only an important keyword, just only an important point, because we would like to listen to what you are going to present. We don't want to read it, okay? It means that you just put very important points into it. Don't have to put everything. Okay, because we have some more time, I would like to show you something a little bit about the time series data. I already posted the data set on Google Classroom is the photo number 3. So I would like to show you the overall data set so you can compare between the time series data and the cross-sectional data. So here, yep, you will see that for time series data, we have year variable here. It means that we collect just only one entitle. For example, like in this data set, it's going to be about the fertility. It's like the number of children born in each year in the United States. So we just collect only the data set in the United States and we collect it across years. So this is kind of like how the time series data set look like. Okay, and then the things that I want to do is that I'm going to request. So my dependent variable here will be the GFR. So GFR is like the number of children who were born in each year, right? And my independent variable here is the PE. PE is the tax, personal tax exemption. And I am also interested in PIL. PIL is like the control PIL, and also the World War II. So World War II is like the period that the United States was in the World War II. So if you opened the data set for PIL and World War II, like WW2, both of them are dummy variables. So PIL here is like the period of time that the birth control were introduced to people. And I would like to just request my dependent variable on other independent variables. This is the result that you will get. So I'm going to go it pretty quick because we do not focus on time series data that much, okay? But I just want to follow the lecture that you have learned. So basically, like the interpretation is the same as the cross-sectional data, but the things that you have learned is about like the data, like the time series data, also have a problem, right? For example, like they might have the auto correlation or serial correlation between each time. Like in this case, I'm going to just plot a graph of the residual. Yeah. So you can see like a trend of their residual. For example, like the first, they kind of like went down and then they went up and then they went down again. So you can see a trend of the residual. It means that this data set might have a serial correlation issue, right? And the formal way to take a look at it is the Durbin-Watson test. We also have it here. And again, if you use Durbin-Watson test, you have to compare the number that you have here with the tables of the Durbin-Watson test, right? For example, like it depends on the number of the observation that you have. They also have like the first column here is the number of observations. And the top row here is going to be the number of your independent variables. And they also have DL and DU that you already have learned in the lecture class. You just use, for example, in this case, we have 72 observations, and we have just 3 independent variables. And I'm going to use just 0.5. So it's going to be this table, just 0.5, with the 72 surround here and 3 independent variables, like around here. So this might be my dl and du. And then you have to compare it with the Durbin Watson that you have here. And the easier way that we can do is just going to the view and go to the residual diagnosis. And we also have the serial correlation LM test here. After you click on it, it will ask you like how many lags that you would like to test. So lags here is like, okay, if you would like to test just only like maybe last year might have an impact on this year. So you can click on just only one lag. Or you might think that, oh, might be like 2 years ago also have an impact on this year. So you can use 2. But maybe I'm interested in 6. Maybe like 6 years ago also have an impact on this year, for example. So the null hypothesis is the non-zero correlation. And again, just take a look at the chi-square here, the observations times with the r-square. And of course, is significant. It means that we can, is significant, it means that we can reject the null hypothesis. So if we reject the null hypothesis, it means that our dataset have a serial correlation issue. So let's take a look at the table below here. It's just only 1 year that is significant. It means that just only the data of the last year that affect this year. It's just only 1 year lag. Okay. If you would like to fix this problem, one way you can do is that if you would like to run regression, you can just go to option and click on the new list. They are going to adjust your standard error. Then click OK. You will get a new result. So I'm going to compare between with and without the adjusted standard error. So for the right one is the original regression. We didn't do anything, but for the left one, we already adjust our standard error. You can see that it's totally different. And of course, once your standard error changes, your t-statistic changes, and also the probability changes. Right? The same problem when you fix the heteroscedasticity in your cross-sectional data. So once we fix it, then again, you might try to reject it whether or not they still have a serial correlation. And again, they still have a serial correlation. It means that we have to find another way to fix it. Besides changing, like adjusting the standard error, you can do the first different. So the first different is that you just deduct minus like the variable from year t with the year t minus 1. So this is the first difference method. Let me write it down. So normally we have y here, right? So it's not yi, it's yt because it depends on time. We have beta 0 plus beta 1 x t, something like that. So the first difference is going to be yt minus 1 here. This is what we call first difference method. So basically we just deduct, just like use the data of year t minus the data with the year t minus 1. Or you can just do something like this. Because the difference can say something like a delta sign. Okay. And how to do that in eViews? So first, you might generate variables in different forms. I mean, like just trying to minus yt minus with the yt minus 1, right? But for me, I'm going to just regress it directly with the difference method. So the things that I'm going to try is the ls, and then because our dependent variable here is the dfr, we are going to use d first. So d here is for difference, and then just type your dependent variable in parentheses. It's going to be dfr, and again we have c. Oh, I'm sorry. It's just the no equal sign. And then also we take difference for the personal tax exemption. And because PU and World War II is just a dummy variable, we don't have to take difference on it. As I mentioned, D here is the difference, is the first difference. So once you're done, just press enter. This is the equation that you got. So they will show you that, okay, you already take the first difference in your dependent variable and also in your independent variable. And because, as I told you, like Pew and World War II, it's just a dummy variable. You don't take it. And if you see that, so at the beginning, before we take the first difference, we have 72 observations. But once you take the difference, of course, they are going to lack 1 year because you use yt minus with the yt minus 1, right? You just use the different years to minus to each other. So that's why your observation will be deducted by 1 observation. So from 72, you will have just only 71. And take a look at the Durbin-Watson test. Is increased significantly. So we are going to just take a look at the serial correlation again. So now we don't have an issue of the serial correlation anymore because the probability is pretty high and we cannot reject our null hypothesis here. Okay, so that's one thing for the serial correlation. Another thing is that we have to check for the stationary, right? For stationary, we are going to check it one by one independent variable. So for example, like in this case, if because like the waste variables that we are using, they are just dummy. So there is only one ratio variable, like the personal tax exemption. So I'm going to just open it. And then we are going to use the, I think it's the unit root test. Just go to view and go to unit root test. Go to standard one. And they will have a test type here. So basically they already set a default as the augmented Dickey Fuller, the one that you have learned today, right? And just click on it. And look at the t statistic and the probability of the Dickey Fuller statistic test. Because of the probability is pretty high. And again, the null hypothesis is your variable, this one, the personal tax exception, has a unit root. So has a unit root here, it means that it's non-stationary. So if you cannot reject your null hypothesis, it means that this variable is non-stationary. So if it is non-stationary, from the lecture, you might try to add the lag of this variable. So how to generate a lag of this one? And again, we are going to use series to generate new variable. And I'm going to use PE and lag. Use equal sign and then use PE, and in parentheses, I'm going to type -1 here. So we are generating a 1-year lag of this variable. Use equal sign and then again type the PE. PE is the variable that we would like to generate a lag. And -1 here is we are going to tell the evils that just generate only 1 year lag. So if you would like to have more than a year lag, you can just change the number here. So if you would like to do like 2 years lag or 3 year lag, you can just change the number. Okay. And then press enter. You will have a PE lag here. So I'm going to just open PE and PE lag together. You'll see that, okay, like the first 4 rows is equal to 0. So I'm going to just like check with the 5th row. So for 5th row, before we take a lag, our original PE is equal to 19, right? But you can see like 19.27 will be in the 6th row for the variable that we already take lag here. So basically it's just like lag 1 year. So if you take 2 years lag, the 19.7 here will be on the 7th row. So it's going to be like 2 years lag for each number. And again, you can just request our dependent variable with the personal tax exemption and personal tax exemption that you already lacked 1 year with another 2 dummy variable here, for example. So this will be the result. Do you have any question about it? I know I'm going pretty fast, as I mentioned before, because we do not focus on time series. I just want to show you what you have learned in class and how to apply it into real data set, and that's all. And actually, that would be all for the time series. I spent a lot of time to explain you about the cross-sectional data, trying to review again before you have an exam. Do you have any question? Actually, I don't mind if you don't understand anything about the time series, but I kind of like want you to understand about the cross-sectional data. Do you have any question about it? Okay, so if all of you don't have any question left,
อาจารย์ครับ there are questions in the chat box ครับ
okay. Could it be like only one independent variable in a log form while other independent still are in normal form? Yes, of course, you can do that. But again, please be careful when you interpret the data, interpret the coefficient, because they are going to be in different ways to interpret it.
Professor, do we have to wait for the class to end before asking about the projects?
Oh, it's already end. I mean, like you can ask,
alright.
you can ask some question about it. Okay.
We have 4 questions from our group. So our first